Oh, am I? Waiting in the lobby.
It's coming.
Just like
Hello, everyone. Can you hear me okay? All right. Uh, yeah, sorry about not being able to make it in person, and thank you for accommodating this remote session. So what I'd like to do today is go over some of the things about LARSA that you might use in this upcoming homework. Again,
Excuse me, Professor?
yes.
Yeah, could you, we're in the room right now. Could you
Uh-huh.
possibly give us the ID number so we can put it on the projector?
Oh, um, the classroom access ID?
Yes, sir. I believe it's, yeah, the meeting ID.
And the passcode.
Yeah, and if there's a
Oh,
passcode. Thank you.
well, I think the Um, best way to do it is for maybe for you to open your email and click on the link at the computer in the front.
HDMI.
Okay, thank you.
So do you want me to give you a couple of minutes while you do that?
Yes, please.
Okay, sure. So while we wait for that, does anybody else have any questions? Let me know when you guys are ready. All right. shall we start?
Yeah, we're all good.
All right, excellent. All right, again, thank you for accommodating this, right? So, like I said, we'll start looking at LARSA as it applies to your upcoming homework, okay? And as I was saying in the first class, the way we're going to learn it is not something that's very particular to LARSA. Just any structural analysis software will function in this way. So, using structural analysis software. So generally there are many steps. We can kind of think about it as input analysis, sometimes this is called pre-processing, this is called post-processing sometimes. Okay. And the input itself consists of geometry, properties, loads. Okay. And you guys have probably seen this in 323, either in the context of LARSA or SAP 2000. So what we're doing here is probably not going to be very different. And then analysis, it could be many types. There could be just a static analysis. There could be a dynamic analysis. There could be a construction type analysis where you're doing one thing, following the next, things like that. Okay. And then so coming back to geometry, usually there's joint coordinates. And member connectivity. And support conditions. Now, in more advanced software, for example, finite element software, this geometry construction may not be done manually. So you may have like a high level geometry, and then there may be some automatic meshing tool. So for example, maybe you have a part that looks like this, some kind of a complicated part with a hole in it, something like that. And then what you do is simply create the geometry of this part, and then the software will automatically break this part into what are called finite elements, different shapes like this. And, it'll automatically generate, these are joints, these are elements or members. So the software will automatically generate the joint coordinates and connectivity of the members, things like this. Okay. So for our purposes, for the most part, we will do this stuff manually. Any questions up to this point? Then once we talk about this, we'll get into the software and show how these things are. Okay. So properties is usually material properties. Things like modulus of elasticity, things of that nature. And then section properties. For members like beams or truss members, things like that, the section properties will just be things like area, area moment of inertia, things like this. Okay. So loads could be static. Okay, and static loads could be point loads, distributed loads, and also support settlements. Loads could also be dynamic, like, for example, an earthquake ground acceleration, but we will not look at. Oh, when did I stop? I seems to have somehow accidentally mute. Can you hear me now? Okay. All right. So like I was saying, different types of loads. For the purposes of this course, we'll mostly deal with static loads. Maybe some construction analysis, things like that, but we won't do any dynamic analysis. When we get to bridges, we'll do some construction type analysis, but we won't do dynamic analysis or dynamic loads in any of the homeworks in this course. Okay. So with that, let me switch to LARSA here. Okay, so when you first start LARSA, you'll have something that looks like this. I'm going to close that, and there's this new project here, right? So I'm going to save that project in wherever I want it to be, but I'm going to just save it in under LARSA projects. SCA 324. Okay, and so following that sketch that I made, the first thing to do is to create a geometry. So what I'm going to do is stop sharing this again for a second. The example we're going to do is a simple frame like this that is fixed here, fixed here. This distance is 20 feet. This distance is 10 feet. Okay, later we'll see that this is maybe something like that. Okay. And then these columns it's a steel frame. These columns are W8 by 31, and the beam is W16 by 40. And then we're going to apply different load conditions, which we'll get to. Okay, so what we're going to do is I'm going to number this joint 1, this joint 2, this joint 3, and this joint 4. And then I'm going to number this member 1, 2, and 3. Okay, so what are the joint coordinates? Joint 1, let's make this the origin. So I'm going to call it 0, 0, 0. So I'm going to model this in the XZ frame, XZ plane. Okay, so this is 0, 0, 0. And then 2 is 0, 0, 10. Joint 3 is 20, 0, 10. And joint 4 is 20, 0, 0. Okay, any questions up to this point? And then the members, member 1 goes between joint 1 and joint 2. Member 2 goes between joint 2 and joint 3. And member 3 goes between joint 3 and joint 4. Okay. And this one is fixed, and this one is fixed. Okay. So that's the geometry we're going to model. So we're coming back to LARSA now. Okay, so there's a number of ways to input these things. You can actually draw it over here on the screen. You know, you can select joints and you can go and draw it on the screen. But the way I like to do it is using the spreadsheet. So I just go input data, geometry. Okay, and I get the spreadsheet and I can just put in the numbers directly there. Okay, this way I feel like I don't have to learn various features of the software, like where to click and stuff like that. This may not be the most efficient. You know, if you're going to use this software day in and day out, then you may discover more efficient ways of doing things. But, you know, I'm not going to, I'm going to focus on things that are universally applicable, not things that are specific to LARSA, like you can click this and do that and stuff like that. So this is something that will always, you know, be applicable, right? So you make sure the units are right here. Okay, some software have units, other software just have to make sure, you have to make sure that the units are consistent. In LARSA, it uses units. So joint 1 is 0, 0, 0. Joint 2, we said is 0, 0, 10. Joint 3, we said is 20, 0, 10. And joint 4 is 20, 0, 0. Okay. Now, if we go over here and zoom extent, okay, we're gonna see those joints, I think. And if I do a show joint number, okay, we see that it's joint 1, 2, 3, 4 creating. Okay. And then I'm going to go and apply the boundary condition. So I'm going to fix joint 1. I'm going to fix all the translational degrees of freedom. And I'm going to fix all the rotational degrees of freedom. And I'm going to do the same thing for 4. Okay, so if I come back here, I'm going to see that it drew some support conditions there, you know, representative of the fixed support. Okay, any questions up to this point? Can you guys also hear me okay and stuff like that? Okay. All right. So one other thing that we can often do is if we know that the structure is going to be in a two-dimensional plane, for structures with a few degrees of freedom like this, it doesn't matter. But if we have a very large structure and we know that it's going to be in 2 dimensions, it may be helpful to go and fix all the out-of-plane degrees of freedom. Okay, we're not going to do that here, but if we want to do that, there is an option called universal restraints. And for example, if I go to constrain the structure in the XZ plane, okay, what do I have to fix? I have to fix the Y translation, I have to fix the X rotation, I have to fix the Z rotation, because any of this will result in out-of-plane deformation, right? So if we know that the structure is going to be in 2 dimensions and we want to restrain out-of-plane degrees of freedom, then we can do that using this universal restraint. So I don't have to go and apply to each joint. It'll get applied to all the joints. Okay, any questions on that? Okay, so I need to save this. And now I'm going to go and add some members, okay? So we said member number 1 goes from joint 1 to joint 2. Member number 2 goes from joint 2 to joint 3. Member number 3 goes from joint 3 to joint 4. So if I now go and look at the graphics, okay, it would have updated with some numbers. Okay. Now we have to input some properties. So let's go input data properties. So there's material properties and section properties. So I can just go and directly enter, for example, steel. Okay, modulus of elasticity is 29,000 KSI. Poisson's ratio for steel is 0.3. Okay, and I can do that like that directly, right? Or I can also go to input data materials, and I can import an existing material. So for example, I can import A36 steel. Okay, and you see that, the elastic properties are the same for all the steels. What will change is things like yield stress. Okay, yield stress is the imported steel is 36 KSI. Ours is showing is 0 because we just didn't put that number in. And that's not a number in this analysis we're going to use, so we can simply ignore that. But, I'm going to delete this one, the one we created, and then keep the one that I imported. Okay. So the reason I did that myself and then imported is because if there is a material you want to use that doesn't exist in the LARSA database, you can always just create it and manually input the properties. Okay. So for example, if I have a steel whose yield stress is 100 KSI and it's not in the database, I can just input it myself. Same thing, I can go and input section properties myself also, right? I can just go and just say, my section, and then start putting in the area and things like that if I have a cross section that's not in the LARSA database. But I'm going to just import our 3 cross sections that are in the LARSA database. So sections. And I'm going to import the 8x31. And I'm then also going to import the 16x40. Okay. Any questions up to this point? So for the swing set frame in the homework, you're looking at pipe sections. You can either import something close from LARSA's database, or you can just, I gave you the tables on UBLearn, so you can just look at the properties and put them in manually. Either way will work. Okay. Any questions? Let's see if there is anything in the chat or anything like that. And listen. Okay, nothing. Okay, all right. Okay. So let's save this. Okay, there's one thing now that we want to make sure is done correctly. This doesn't happen very often when we're doing 2D stuff, but in 3D we have to make sure this is right. Okay, so let's look at this, and I'm going to go to graphics and do complete rendering. What happened here? Oh, sorry. Before we do that, we have to assign the properties, right? So, okay. So we imported the properties. We have to assign them to the members, right? So I'm going to assign that all these members have the same material, A36 steel. And then this is the column, so I'm going to assign the 8 by 31. This is also a column, I'm going to assign the 8 by 31, and that's the beam, so I'm going to assign the 16 by 40. Okay. Any questions? Okay, so when we go over here, and I do, what's happening here? All right, let's do like this, okay? So show. I'm not sure what's happening there, but thing's not displaying properly over here. Sorry. Okay. Well, there's a nicer way of looking at it. I'm not sure why it doesn't work, but if you generally if you go and do complete rendering, it should actually show you the eye sections, and it's easy to look at that way. But this is what I want to point out, right? So so member orientation. Okay, so let's for example consider this member here, right? Consider that member. We assigned it to be a W16. Okay, W16 by 40 is a cross section that looks like this. It's called a wide flange section. We'll learn more about these when we talk about steel members, but the cross section looks like this. Okay, it's a now when I look at it with the x-axis this way, the z-axis this way, and the y-axis this way, right? When I look at the frame like that, do I want the eye shape to be like this? Or do I want it to be like this? Do I want case 1 or do I want case 2? Anyone?
1.
Yeah, 1 because, we want the beam to be bending about the axis, this axis, which has greater moment of inertia, right? And greater strength. Okay, so we have to, in fact, there may be some structure that is not quite located in the XZ plane, and we may want the member to be oriented in some arbitrary angle, like this, right? that is neither horizontal nor vertical, but something rotated. So we must be able to specify what the orientation of the cross-section must be. And for that, there is this input parameter called orientation angle. Okay, and the way that works is we take the structure. So for any member of the structure, this is the global x-axis, the global y-axis, and the global z-axis. Okay, this is called the global coordinate system. And joint coordinates are specified in this global coordinate system, right? But in order to specify which way the cross-section is oriented, and in order to specify member loads, loads that are in the span of the member, things like that, we construct something called a local or member coordinate system. Okay, so an axis from joint 1 to joint 2. So if this is the first joint of the member, and this is the second joint of the member, as we specified in the connectivity, right? So for this member, we specified that it goes from joint 2 to joint 3. So this is the first member, and this is the first joint, and this is the second joint. Had we specified the members going from 3 to 2, then that would have been the first joint, and that would be the second joint. Okay. So the local x-axis is pointed from the first joint of the member to the second joint of the member. This is the local x-axis. Okay. And then the local z-axis to start with is such that this is in the local x, global z plane. Okay. Starts out this way. And then there is a parameter called orientation angle. That says how much the local frame, local coordinate system is to be rotated about the local x-axis. Okay. So to start with, x is that way, local z is kind of lined up with the global z, and local y is in this direction. But the orientation angle tells us how much this needs to be rotated, so we get the orientation that we want. Okay. Now the convention is for an I section, this is called the local z-axis, and this is called the local y-axis. The local z-axis is the strong axis, and the local y-axis is the weak axis. Okay. Strong means has greater moment of inertia and greater strength. Okay. So now going back to LARSA. So you see that local x-axis is pointed this way. Local y-axis is pointed this way, and local z-axis is pointed this way. Okay. I mean, I'm saying this is x, this is y, and this is z based on the color notation here. Okay. There's a better way to do this, but for some reason it doesn't I can't get it to go. So we'll just do with this, okay? So this is the local X, this is the local Z, and this is the local Y. So the strong axis is going this way, right? The strong axis is going vertical. So the beam is, lying flat. But we said we want the strong axis to be horizontal. Okay, so I go to members, I go to member number 2, and I make the orientation angle 90 degrees because I want to rotate it 90 degrees. So when I go back here, you see now that the local z-axis is going this way, and so the member has the right orientation. Okay, any questions on this? This is maybe a little bit tricky when you see it the first time. But do you see why I want to make the orientation angle 90 degrees? Basically because I want to orient the cross section in such a way that the strong axis is horizontal and the weak axis is vertical. Okay, and I'm going to do the same thing for the other members too, because I want them to be that way. Okay? So I'm going to, in fact, select them all and make them all 90 degrees. Oh, I see why it didn't work before. Okay, so let me, I put section at end instead of section at start. That's my problem. Okay, all right. Things are going to be okay now. Here, I'm just going to say same as start. So LARSA also allows the cross-section to change over the length. So I accidentally put the section at the end instead of at the start, okay? But I'm just saying that the end section is the same as start, so it's a uniform section. So if I go back now, I think it should, okay? So if I do complete rendering, I should see what it looks like, okay? Yeah, this is what I wanted to show you earlier, but I screwed up, so I didn't show up properly. Okay, so if I hadn't done the orientation as 90 degrees, if I change that back to 0, okay, and I go and look, okay, you see that it's oriented the wrong way now. Okay, does that make sense? Any questions? So if the cross section is rather straightforward, like a W section, wide flange, or call it I section, and the structure is in one of the coordinate planes, it's in the XY plane or XZ plane, then the orientation angle is often 0 or 90. There's nothing else, right? But if the structure is three-dimensional and the member is in some plane that is not the coordinate plane, then the orientation angle needs more careful attention. Okay. Any questions? Okay, so we've done geometry. Basically, we did joint coordinates, member connectivity, and support conditions. Then we also did properties, material properties, section properties. We assigned the section and material properties to the members. And then we had to do this orientation angle, to get the proper orientation of the cross section of each member. Okay. Any questions up to this point? Okay, so I'm going to save this, and we're going to start doing loads. Okay. So I'm going to do load here, and then I'm going to add a load case. And for now, we'll just leave it as load case 1. And what I'm going to do is I'm going to add a 10 kip load about a third of the way here, and I'm going to add a 10 kip load about a third of the way here. Okay, so I'm going to do that again with the spreadsheet. I'm going to do it as a member load. Okay, member number 2, type point force, direction global Z, and I'm going to do 10 kips in the downward direction. So it's minus 10 kips. Okay, again, pay attention to the units. Okay, LARSA uses units, and we want to make sure that our input is in consistent units. Okay, there's also a way to go and change the units here, but I'm not going to do that. I'm just going to leave it. Okay, so start position is I'm going to do 0.33. So that way it's a third of the way, right? So if we go to the graphics view, we should see that 10 kip load here, right? Then I'm going to do another 10 kip load. On member 2, in the global Z, another 10 kip load. Now I'm going to do it at 0.67. Okay, so everybody see why I'm doing 0.33 and 0.67? So I get it a third of the way through the length of the member, 2/3 of the way through the length of the member, right? So we see this one here. Okay. Okay, so I'm going to save that. In this case, that's all we're going to do. Fairly simple. And we're going to run analysis. And you see that there's lots of different kinds of analysis here. Later, we will do things like stage construction analysis when we do bridges. And we may also do a couple of other things here. But for now, we're just going to do linear static analysis. Okay. Linear static analysis is pretty much the only kind of analysis that you did in CI 323, right? So that's what we're going to do now. But as we go forward, we'll do some other kinds of things like stage construction and things like that. Okay. Any questions up to this point, what I'm doing? I mean, I know this is not very conducive to stopping and asking questions, but to the best you can, please do. Okay, please stop and ask questions. Okay, so you see here that there's a box that says perform quick integrity check, right? If I made some mistakes in my modeling, things are not consistent, okay, it's not going to catch fundamental problems. But let's say I have a member without a joint connected to it, or I have a member without assigning properties to it, things like this. This consistency checks, right? This doesn't mean my model is correct. It just checks for internal inconsistencies. And if there is an inconsistency, it'll list what the inconsistencies are, and that's helpful information. So if it tells you there's a problem, you can just click on it and see what the problem is. I don't know if there's any problem here. Let's just run it and see what happens. So I'm going to say analyze. Okay. Okay, and it did the analysis. Okay. So we could do different things. For example, we can see what the reactions are. Okay. So the way to do it is I go to results, spreadsheets, joint, and reactions. Okay, and I have to go and select a load case to see the reactions. Okay, and we see that, obviously the Z reaction, both the joints, the Z reaction, both the joints better be 10 kips, right? Because of symmetry, they better be 10 kips, and they are, okay? Okay. And there is also a moment about the y-axis and a small reaction in the x-axis. So this is how we look at reactions. So in the swing problem, if you want to look at the reactions at the support to check for overturning, this is how you would check for reactions, right? So you go joints, results, spreadsheets, joints, and then reactions. Okay. We can also look at things like moment diagrams. I think that's what it is. Member forces. Let's go back to the simple rendering. Okay, you see that there's a very, very tiny bit of axial load here, but there is a 10 kip axial load here as we expect in the columns. I'm saying axial because that's what that is, right? Can anybody tell me why it says axial FX? So the axial force in this member, you would think it's in the z direction, right? But it says axial fx. Can somebody tell me why it says fx and not z? Anyone? So you see that the local x-axis of this member is actually lined up with the global z-axis, okay? And all member forces are reported in the local coordinate system. So axial force for this member is actually Fx and not Fz because axial force for this member is in the local x direction, okay? Now, if I want to look at bending moment, what direction should I look? Should I look at bending moment about the y-axis or bending moment about the z-axis? So you see that local y is this way. Bending moment's actually about the local z-axis. So if I look at bending moment about the y-axis, I won't see anything, or some small, round off kind of thing. But if I see bending moment about the z-axis, then I see the type of bending moment that I like to see. Okay, have this straight line, straight line, straight line bending moment. Okay, now look at this one. If you look at the loads, is the bending moment here? Okay, it is automatically positive. It's done the right way. Okay, all right. Okay, so sometimes it may be because of a um, okay, so LARSA may by default show the bending moment diagram like this, okay? Because some engineers like to see the bending moment diagram. They call it bending moment in the tension side. Because this bending moment diagram sort of looks like the deflect shape. So LARSA will by default show it like this. So you have to go to results and then result display settings and then member force diagram, say invert, okay? And then it will show it the way that we're used to seeing it. Any questions up to this point? Okay. Now, what we would also like to see is some displacements, okay? Now, LARSA doesn't do a very good job of showing displacements when I don't have sufficient resolution in the shape. I'll tell you what that means in a second. So if I look at displaced shape, I don't see a whole lot of stuff, okay? So in order to see better displaced shape, although I can see joint displacements in the spreadsheet, I can go and see spreadsheets, joint displacements. And then for load case 1, I see some small amount of X translation and, small amount of Z translation and Y rotation, right? But if I want to get a better picture of the displaced shape, I'm going to break these members up a little bit. Okay, so let's see here, modify. Okay, I'm going to go and do break members. So first, what I have to do is maybe unselect all the members. There's a tool here that says unselect. Okay, so I can, unselect. I unselect all the members. And then I can select only the members that I want to break. Okay, so maybe I just want to select this member and this member. And I want to break those two members into two pieces. So modify break members. I'm going to break it into two pieces at half the length. In fact, maybe I break it up into three pieces at the third of the length, okay? So LARSA will automatically create the joints and all that kind of stuff to achieve that, okay? So I've got now three members here. If I go to my member spreadsheet, I got a bunch of more new members here. Okay. Any questions on what I did here? Okay, so now I'm going to unselect those members that I broke. And I'm going to break this member into 2 pieces. Modify, break members. I'm going to break it into 2 pieces. So I got another joint over here. So notice that joint number is 9, okay? That joint number is the new joint that it created in order to break this member is joint number 9. Okay, so I'm going to do now, I think, select all or something like that. So I get everybody back, I think. Okay, I got everybody back. And I'm going to run the analysis again, but now it's going to report displacements at all these new joints that I created, right? So let me save that. I'm going to run analysis again. Okay, if I now look at displaced shape, okay, you see that I'm getting a little bit better. If I look at the front view, I'm getting a little bit of a better representation of the displaced shape because I have more joints to capture the displacements. Okay, the answers are the same as they were before. But just because I have more resolution to capture the displacements, I'm getting a more reasonable looking shape. Okay, if I draw a moment diagram, I'll still get the same answer. Okay, same answer, right? Now, let's say that I want to determine the displacement at this joint. I can go now to results, spreadsheets, joint displacements. And then we remember that joint was 9. So you see that there is a Z translation of a 1/4 of an inch there, right? So I'm able to capture the largest displacement by doing that, okay? So when you do if you want to, for example, calculate the displacement in the beam of your swing set, this is how you may want to do it. You introduce a joint there so that LARSA will report the displacement there, and that's the easiest way to get the displacement, okay? Any questions? So we looked at the moment diagram, but we can also look at actual
There's a
values.
question in the chat.
Yes. Oh, is there a question in the chat? Yes. Thanks for pointing it out. Let me see here. Oh, can you show how to break up members again? Okay, all right. So, okay, let me break this member again artificially into 2 and this one into 2, okay? So I'm going to unselect everybody first, okay? So I'm going to unselect all. So I have now nobody, okay? And then I'm just going to select this member, the member that I want to break. Or, if I want to break a bunch of them, I can select all of them at once. And then I go to modify, and then break members. And then I want to break it into 2. Okay, so it created a new joint number 10. So I have 2 members here now, actually, where I used to have 1. Okay, now I can, unselect everybody and then select this one, maybe. And then I want to break that into 3, modify, break members, break it into 3. So I got 3 members there. And then I do select all, and I see everybody, okay? So the idea is basically you select the member you want to break and then say modify break and how many pieces you want to break it into. And none of this should matter for the results. So if I run this with all these broken up members, I should still get the same moment diagram and things like that, okay? Right? So we can look at results graphically this way, but maybe we also want to look at it, actually get numbers because that's what we need, right? So let me show what the member numbers are. So this member is number 2, okay? So from this picture, I'm seeing that this member is member number 2. Member number 2 goes from join 2 to join 10, right? If I go to members and I look at member number 2, it goes from join 2 to join 10. All of this must be consistent, right? And let's say I want to know what the bending moment here is, okay? So what do? I go to results, spreadsheets, member forces, member end forces, local, okay? We want local. And I'm looking at the Z moment, okay? And I'm looking at member number 2. It has the 2 joints, number 2 and number 10. And you see that the bending moment about the Z-axis is at 2, it is 19.45. Maybe a little bit of sign issue there. Okay, 19.45. Not exactly sure why it doesn't show the. Oh, maybe yeah, okay. Yeah, it doesn't. It's not showing bending moment. It's showing member end moment. Okay, this requires a picture. Maybe we talk about it a little bit on class on Thursday. Easier in person than like this, I think. But you see that 19.46, and that's what we see here. Okay, why is it not a minus but a plus here? We'll talk about it in class. Okay, and then on this side it's 30. 30 point something, and we have that. Okay, so we've seen now how to look at the results both graphically and numerically. Numerically, you always go to the spreadsheets, and you just need to know what member end moment means and things like that so that you know where to look it up. Okay. And again, you see that everything is reported in the local coordinate system. So even though this axis seems to be the global y, it's the local z. And so we see, moments in the local z, nothing in the local y, because there's no bending happening about this vertical axis. Okay. Any questions? Okay, so hopefully this gives you enough to get started with whatever modeling work is needed in homework number 2. And if you have any questions, please, send them through Piazza, and I'll try to answer them. I'll try to be responsive. If there are no other questions, maybe we can stop here. And any loose ends to this will tie up in person in class on Thursday. Okay, any questions? Let me check the chat to see if there are any questions there. Okay, no other questions?
I have a question.
Yes.
For how we have to like select our like width of the swing set and stuff like that, how much explanation are you expecting us to have for how we chose them?
Very little, just a phrase or a sentence, just to convey some line of thinking, right? So certainly not a very elaborate, thing. So the types of reasons are functionality in terms of use, and then functionality in terms of structural action, right? So for example, if you want to make it wider, it may be because you want to increase stability. So that's like a structural reason. Or if you want to make it taller, maybe you want the swing to swing slowly or something, and that's a functional reason. But just a phrase or a sentence, that's all. Does that answer your question?
Yes, thank you.
Okay. Any other questions?
There are more questions in the chat now.
Okay, all right. Yes, will the lecture video be available? Yes, I'm going to try to, both the questions are the same. So I'm going to try to post this on UB Learns, hopefully later today. And I set up recording, and I think it is doing it. So yeah, I should be able to post it later today on UB Learns. Any other questions? All right, sounds good. Thank you so much again for accommodating this remote thing. Hopefully it worked out at least reasonably okay. And I'll see you guys on Thursday, I think. Thank you.